So now we're going to cover how you talk to I/O devices. So when we talk about communicating with I/O devices, we need to specify how the CPU specifies the device, the data, and the command. We need to specify when does the CPU know the device is ready, and what does the CPU communicate to the device. So how do we talk to the device? We're going to cover 3 different ways to talk to devices. The first is having special input-output instructions in the processor. The second is having special input-output memory addresses. And the third one is having special input-output hardware that basically takes care of everything for us. So when we ask the question when does the CPU know the data is ready, we're going to talk about 2 ways. So the first one is where the CPU can do polling. That is, it's going to ask over and over again until the data is ready. And then the second one is an interrupt. So in an interrupt, the hardware is going to stop the program when the data is ready and tell it the data is ready. When you talk about what is communicated, well, we're going to have to communicate the data. That is, we're going to have to send and receive data and addresses, and control. So we're going to need to be able to send commands. Do we want to do a read or write, and receive status? And the status is going to be, is the read finished? Is the write finished? Was there an error? So let's take a look at the how here and look at I/O instructions. So an I/O instruction is going to specify a device and a command. So for example, we could talk to the keyboard. And the command we could say, well, we want to do a read or write, and that command is then going to be sent to the I/O bus, which is going to go to the device. So in x86, we have in and out instructions, which do this sort of I/O command. But there's a problem here. This is slow in that we only transfer 1 register at a time, and it's limited to only a few devices and a limited number of commands. So this is not a great solution in general. Another way to communicate is through memory mapped I/O. The idea here is that we're going to take portions of the address space and we're going to map them to I/O devices. Then to access the I/O device, we just read and write to those addresses. So here's our memory space, and we're going to say, well, these 2 chunks of the memory space, they don't actually go to our memory, they're going to go to device 1 and device 2. Now we don't need any special instructions. We just need to know the address of these devices, and we do regular loads and stores. Now if we want to be more specific here, we can have special addresses for commands and status. So we can divide up this data into space, this address space, into space for data, status, and commands, and do the same for the other device. So what's the problem with this approach? Well, it uses up some of our address space. So if you take a look here, if we don't have that much address space for our program, now we've used up some of the area where we could have been storing data by mapping in the I/O devices there. So let's take a look at how you'd implement memory mapped I/O. Here's our CPU and its bus. It has address, data, and control lines. And we're going to put an I/O device on it, an I/O interface. Let's take a look at what's inside there so that it can handle memory mapped I/O. So inside the I/O interface, we're going to have address decoders. And these are going to look at the address that's sent, and it's going to compare to see, does this address match the address that I'm supposed to pay attention to? If it matches the in address, it's going to take in data to write to the device. If it matches the out address, it's going to send data out from the device. And then we'll have addresses for command and status, which receive and send data as well. So the I/O device now needs to watch the address bus to see if its particular address is being accessed, and if so, then it has to pay attention to the control and data lines. Another approach is called direct memory access. And the idea here is it would be better if we had special hardware that can transfer the data for us. So if we had special hardware, then the processor wouldn't have to be involved in this at all. We'd no need to do the reads and writes ourselves, and we wouldn't have to check the status for every word. We could just say, go transfer a bunch of data and tell me when you're done. And this is called direct memory access, or DMA. The idea here is we have this special hardware to do the transfer, and we just set it up. So we tell the hardware which device, which command, how much data, and where to get it or store it. The device then goes off and does all the work. So for example, we tell the DMA engine, go load 4096 bytes of data from the device at address 128 and store it to memory address 384. The DMA is then going to go off, and it's going to execute 1024 4-byte loads, write the data into addresses 384 to 1408, and when it's all done, it will tell us I'm done with the whole transfer. So now the processor has to do much less work because the special hardware is taking care of most of it. And this is why we do everything these days, because the extra transistors we need to build a DMA engine aren't that many. Transistors are very cheap, and the overhead of having to do this all in software is too high. So we can get much better efficiency by using a DMA engine.